Hello, this is pure bending example number one. This example problem gives a beam that is subjected to two end moments, and the beam deflects downwards and has a deflection at the center delta. Measurements show that the longitudinal strain at the bottom surface of the beam is 0.00125 inches per inch. If the distance from the neutral surface to the bottom surface of the beam is 6 inches, then determine the radius of curvature, the curvature, and the midspan deflection of the beam. So we're going to use our equations of bending to solve this problem. So the first thing that I'll do is I'll jump into the equation sheet here, and I look up my equations of bending. I have two of them that are useful now. Sigma is equal to minus m times y over I, and sigma is equal to minus EY over rho. So with those, I'll go over here to OneNote, and I'll start working here, and I'll just write down the first equation that is going to be our starting point. Sigma is equal to a minus E times Y divided by rho. So in this equation, E is modulus of elasticity, Y is the distance measured from the neutral surface or neutral axis of the beam, and rho is the radius of curvature. It's basically the radius from the deformed beam to the center of curvature, and it's assumed that the beam deforms in the shape of a circular arc. So we also know that we have Hooke's law, and sigma is equal to E times epsilon. So I can do some substitution here. E times epsilon is equal to a minus E times Y divided by rho, or you end up with the equation epsilon is equal to a minus Y divided by rho. So into this equation, we can substitute that we have the value of epsilon is equal to 0.00125 inches. And we can also substitute in the value of y. So we could say that y is equal to a minus 6 inches. And the reason that it's negative is because we take y as positive up. So if I go in and I sketch a cross section here like this, I don't know what the shape of that beam looks like, but let's just assume that it's a rectangular shape like this with some base dimension b and some height h. Then this dimension here is the y dimension taken positive up, and this would be the neutral axis or the neutral surface of the beam. So when we look at the strain that is measured down here at the bottom surface, epsilon, then the distance y from the neutral surface is equal to 6 inches, but since it's in the opposite of the positive direction, then y is taken as negative 6 inches. So what we can do then is we could say that epsilon is equal to 0.00125 inches per inch, and so we end up with this equation: 0.00125 inches per inch is equal to a minus 6 inches divided by rho. And from that we can solve for rho, and we get that rho is equal to 4,800 inches, or we could say that that's equal to 400 feet. Okay. Now the equation for kappa isn't given on your equation sheet. We have rho as the radius of curvature, and kappa is just referred to as the curvature, and it's equal to 1 over rho. So if we take 1 divided by 4,800 inches, then we end up with kappa equal to 0.0002083 per inch is the unit. It's kind of a goofy unit. All right, so that was probably the more straightforward part of the problem. That gives us the radius of curvature and the curvature. So what I'm going to do now is scroll down a little bit, and I'm going to sketch in the deformed shape of the beam. And I'm going to again go with the assumption that the beam deforms in the shape of a circular arc. That didn't work out. So like this, and this would be the support at one end, this is the support at the other end, and then up here I have the center of curvature, we'll call it O. Let me erase that. and then I can draw a line here. This distance is the radius of curvature, rho. This is the original shape of the beam, and then going down here I have this distance and this distance. So this is delta. This distance here is rho minus delta, and then here is a distance that is L over 2. So what I can do is I can just use some geometry. Let me put in some letters here. This is going to be point A. This is going to be point C, and this is point C prime down here on the deformed, and this is B. So if I look at triangle OAC, what I can do is say that the tangent of theta, and this is going to be the angle theta right here, I can say that the tangent of theta is equal to the opposite over the adjacent. So the opposite of that triangle is L over 2, and the adjacent is going to be rho minus delta. Then from that, I could say that the displacement delta is equal to rho minus L over 2 divided by the tangent of theta. Now from the same triangle, I can also write that the sine of theta is equal to L over 2 divided by rho. It's equal to adjacent over hypotenuse. So the adjacent is here, the hypotenuse is there, so we end up with that. So I can do some substitution there. I know that the span length is given in the problem statement as 16 feet. There are 12 inches in every foot. And then we can divide by the radius of curvature. We solved for that as 4,800 inches. So then we can take the arc sine and we can determine that the angle theta is equal to 1.146 degrees. So then now I can substitute back into my equation up here, and I could say that delta is equal to 4,800 inches, the radius of curvature rho, minus L over 2. So this is 1/2 of 16 feet, 12 inches per foot. And then we divide by here the tangent of 1.146 degrees. All right, so if we push through the math on that, then what we end up with is 4,800 inches minus 4,799.0390 inches. And I have to carry more significant digits than I normally would. If we rounded that off, then we would get a gross error in our displacement. So then finally, we can get the displacement delta is equal to 0.9601 inches. Diagram that I drew using a ruler and a compass and a bit more care. Then you can see how the deflected shape correlates to the geometry that we just worked. So I hope this helps.